Greetings, Panthers. It's Dr. Augustine. Today we are going to be talking a little bit about significant figures. This is chapter 1.7, intro. And hopefully by watching this video, which is sort of like the why of significant figures, and the next video, which is the how of significant figures, how do you use them in calculations, you'll have a pretty good understanding of the role of significant figures and why chemists and physicists and engineers worry about significant figures. And I got to admit, it's not a super obvious topic why significant figures are important. Some people make a huge deal out of it. I'm sort of in the middle, and then some people don't make a big deal at all out of them. So I'm kind of in the middle ground. They are very important. They're not the life and death of me, but we might as well learn how to use them correctly and learn how to use why you're using significant figures. So the whole point of significant figures is to tell you the uncertainty of a measurement and where that uncertainty lies. I'm just going to make up a number. I'm going to say, suppose you use an analytical balance and you measure something to be 5.126 grams. The point of significant figures is to tell you that this last decimal place is where the error lies. And if you've used an analytical balance before, you've probably seen the 5.12 stays the same and the 6 flips around. It goes 7, 8, 5, 4, or whatever. So we might express that uncertainty by saying plus or minus 0.002 grams. Okay, and that would mean that the error or the uncertainty on this measurement is plus or minus 0.002 grams. That last decimal place is where things are changing. So, in other words, we're confident about these first three digits, but the sixth here we're not so confident about. That's where the uncertainty lies. So the way we talk about this, or the way we explain this, is we say, all right, how many significant digits are there in this measurement? And it's really pretty straightforward. We just count how many digits there are. So in this case, it's 4.126 grams, and we would say, or 5.126 grams, we would say there are 4 significant figures, 1, 2, 3, 4. And I'm just going to write sig figs for significant figures. Sometimes it's called significant digits as well. And again, the last place, the last decimal, tells you where the uncertainty lies. Now, you might say, okay, that's not a very big deal. What's the point of that? Well, here's some real measurements. So let's take a look at this. This is a volume measurement. This is supposed to be a graduated cylinder. This is maybe water in a graduated cylinder. There's a meniscus here, and we're measuring the volume of this water. And if you want, you can stop your video right now and see what that measurement is. And meanwhile, I'm going to come up with my measurement. All right, so when I look at this measurement, I'm going to say, all right, this is 4 milliliters. This is 5 milliliters. And these are to the 10th place, 4.1, 4.2, 4.3, 4.4, 4.5, 4.6. All right, so it looks apparent to me that it is less than 4.6, but more than 4.5 milliliters. So this is going to be 4.5. And then what we do is if you look at this, you can say, well, that line is definitely underneath the 0.6 measurement, right? But it's definitely above the 0.5 measurement. So that line tells us where the uncertainty lies. And I'm going to say this is 4.58. You might argue with me and say, well, wait a minute, that's actually a little bit higher than that. That should be 4.59. Somebody else could come along and say, well, that's actually 4.57. Somebody might say it's 4.56. Nobody's going to say it's 4.6. So you get my point here? The last digit here, this 0.8, we can argue about. All right, and we could say, it's not actually 4.58, it's actually 4.57. And we could probably assign an uncertainty. And the way we would do this is we'd have to take a lot of different measurements. So let's say we took everyone in an entire class and had them write down on a piece of paper what that number is, and then turn it in, and we'd take an average, and we might get something like plus or minus 0.01, 0.02 maybe, 0.015. That would be the uncertainty of this measurement. So this measurement would have 3 significant figures. 1, 2, 3. Now, why is that important? What's the big deal with that? Well, if we had a different measuring device, let's say we had a beaker, and sadly, I don't have a picture of a beaker, but that might look something like this. And that might have 10, 20, 30, 40 milliliter markings on it. And if we had liquid in the beaker that was something like that, we might say that's like 25 milliliters. Okay, but you certainly can't say it's 25.1 milliliters or 25.4 milliliters because we only have markings to the 10 milliliter mark. So because these are only to the 10 milliliter mark, we certainly cannot say to the 10th place. So where this error ends up, here it's to the thousandths place, here it's to the hundredths place, here it's to the ones place, that tells you something about the instrument that you're using to measure this. Okay, so if you're trying to get a really accurate volume measurement, a beaker is not a good tool to use because that's only going to be marked to the maybe 5 milliliter increment, but not to the 10th place. This one's marked to the 10th place. So if something's marked to the 10th place, it allows you to go one more decimal beyond where it's marked. Let's take a look at this number. Let's take a look at this instrument right here. This is not an analytical balance, but this is a balance, and it's got an internal gear here. This would be in grams, and we're trying to line it up with this 0 right here. So why don't you take a second and see what kind of measurement you get for that. In the meanwhile, I will switch pens and I will write mine down. All right, so I'm going to say 1.28 grams. There's the 1, these are the tenths place, 0.1, 0.2, 0.3, 0.4, 0.5. It's definitely less than 0.3, definitely more than 0.2. So I say 1.28. You might be looking at that and go, well, that looks like it's right in the middle to me. That might be, to you, that might be 1.25. That might be 1.24. That line is almost as wide as the whole marking range here. So in this case, our error might be plus or minus 0.05. Might be a much bigger error measurement on here than it is on this one. This one, we can pretty clearly tell that's less than 0.6, considerably more than 0.5. So saying 0.8 or 0.7 is reasonable. Saying 0.2 is not reasonable for this measurement. Saying 0.2 for this, that's actually not crazy. I mean, it's probably more than 0.2, but it looks to be closer than the 0.3 range, but not much, okay? So this number here tells us how good our instrument is as well. The first number tells us how accurately can we measure this. The second one tells us how good is the instrument that we're using to measure this. Again, a beaker, not a very good way of measuring volume. If you're trying to quantitatively measure volume, if you're trying to hold a liquid, it's fine. But if you're trying to quantitatively measure it, like getting a number out of it, a beaker is not a very good way to do it. If you want to measure the mass of this is okay. If you have an analytical balance, it's even going to be better. All right, so let's count the sig figs up for this guy. So this is 1, 2, 3 sig figs for this measurement. This volume measurement only has 2 sig figs. Okay, so we've taken a look at several different things and several different measuring tools, and we've gotten different significant figures out of them. Now, what you should be getting out of this whole discussion is that the significant figures tell us something about how good the measurement is that's being made. All right, now let's take a look at some other factors related to significant figures. All the numbers I happen to have chosen did not have any zeros in them, but zeros can be kind of complicating. Like there's no zeros in any of these numbers. Zeros can be a little bit complicating. So let's start with a number like this, 200,152.1. All right, so a number that looks something like this, in other words, you have internal zeros here. If you have internal zeros, those count as significant figures. So this would be 1, 2, 3, 4, 5, 6, 7, 8 significant figures. All right, let's just recap that again. If you have zeros in the middle of a number, those count. I'll give you another example of this. something like that, that 0 counts. 1, 2, 3, 4, 5, 6. All right, 6 sig figs on this one. If we have a trailing 0 after a decimal place, let's say this is like 2.130 milliliters, that counts. We have a decimal place, we have a trailing 0 after the decimal place, that counts. So this number has 1, 2, 3, 4 sig figs. Okay, let's recap what we got here. A 0 in the middle of a number counts. A trailing 0 at the end of a number counts. If we had 2.1300 milliliters, that's going to be 5 sig figs. 1, 2, 3, 4, 5. Both of those zeros are going to count as trailing zeros. All right, what if we have a 0 as a placeholder? So in other words, it's a decimal, 0.00381 grams. So these are zeros as placeholders, right? They're holding that decimal place. These do not count. So my number here only has 3 sig figs. Okay, 0 as placeholders do not count. Give you one more example of this. All right, here's a measurement in micrometers, 0.050308. I purposely put some zeros in the middle. This leading 0 does not count behind the decimal place, but these zeros inside do count. So this number would have 1, 2, 3, 4, 5 sig figs. Okay? Next scenario, what happens if we have a number like this? 100.0350. All right, now we've got digits in the middle, we've got digits after the decimal place, we got digits trailing zeros, but you notice we don't have zeros as placeholders. This 1 means that these are not placeholder zeros. So all of these are going to count. 1, 2, 3, 4, 5, 6, 7. And let's take a look at another example. Let's say we have something like this, 200 milliliters. Okay, this number is actually a problem because I have not specified this. I have not put that there's a decimal place here. So this is actually an ambiguous number. And I'm going to encourage you not to write numbers this way. The reason why it's ambiguous is I don't know if the uncertainty is in this place, or in this place. It depends on the instrument as to where the uncertainty lies, but I don't know which of these 3 decimal places there's uncertainty. So because I haven't specified this is ambiguous, and this is not a good way to report this number. Now, if I had put a decimal place in here, this would tell me that all of these numbers are significant digits. And this is actually 3 significant figures if I had put a decimal place. But because I did not put a decimal place in there, I don't know which one's significant and which one isn't. So this is really a bad way to report a number. A better way to do this would be to write it in scientific notation. In fact, if you write a number in scientific notation, there's no question as to what the number of significant figures is. If we write this number, 200 milliliters, as 2.00 times 10 to the 2, what we're implying is there's actually 3 significant figures. If we had written this as, so the way you just count the digits on this side of the number to find the number of significant figures. So 3 significant figures for this notation. If I had been meaning to say this is 200, but it's really the tens place where the uncertainty is, we could just say 10 to the 2, 2.0 times 10 to the 2. And if I just wrote 2 times 10 to the 2, that's saying there's only 1 significant figure. So this is 3 significant figures, 2 significant figures, 1 significant figure. And there's no question now with this number what I'm implying depending on the way I write it. So if I wrote this, I'm saying the tens place in this number is where the uncertainty lies. So that might be like recording a volume with a beaker. I'm estimating to the tens place. That would be true if I wrote this number out. If I was trying to say the ones place is where my uncertainty is, this is the way I would have to write this out in scientific notation. So the summary of what I'm saying so far is scientific notation is really a better way to write out the significant figures because you don't have any question when you write it out in scientific notation. These numbers you can get away without it because there's no ambiguous numbers. It's only when you have a case like this, like 200 or 150 or something like that, and you're not sure where the significant figures are. And for our last thing, let's take a look at a special case, and these are called exact numbers. So this would be something like if we had 12 eggs, or if we have 126 coins, or if we have 12 inches equals 1 foot, or if we have 100 centimeters equals to 1 meter. Notice what we have in all these cases I've just chosen here. If we have 12 eggs, we have exactly 12 eggs. No more, no less. We have 126 coins, we have exactly 126 coins. These are exact numbers. 12 inches equals 1 foot. That's the definition of 1 foot. 12 inches is by definition equal to 1 foot, and 100 centimeters is by definition equal to 1 meter. How many sig figs does this have? Each one of these cases have an infinite number of significant figures. Because we could say 12.000000 all the way out to infinity inches is equal to 1.0000 all the way out to infinity feet. Okay, that's just the definition. So each one of these cases, we have an infinite number of significant figures. This will become important in the next video when we talk about doing calculations. But you should be able to look at a number and see how many significant figures there are. And some of these cases where you have an exact conversion, that would have an infinite number of significant figures. All right, so why don't we quickly take a look over here at some numbers. And this is a good place to stop the video. You can stop the video and count how many significant figures there are. I'll come back in a minute and answer these. All right, so number one here, these are leading zeros, so we don't count them, but we do have to count the trailing zero. So this one has 1, 2, 3, 4. This one has 4 significant figures. This guy right here has only zeros in the middle. 1, 2, 3, 4, 5 has 5 significant figures. 1 decimeter or 10 decimeters equals 1 meter. That's a definition, okay, that there are 10 decimeters in 1 meter. So those are infinite or unlimited, in this case, unlimited number of significant figures. This one here is written in scientific notation to begin with, so we just count the digits on this side of it. 1, 2, 3, 4. This one has 4 significant digits. And this one, all of these are placeholders except that last digit. So this one only has 1 significant figure. All right, so with some practice, you should be able to find how many significant figures you have in any number, and they will become important in the next video when we talk about using significant figures in calculations.